Good morning or good afternoon, distinguished chairs, scholars, and fellow participants. My name is Aiqi Wang from the North China University of Technology. It is my pleasure to present our study entitled A Study on the Dynamic Relationship between Chinese and US Carbon Market Prices, based on a threshold vector autoregressive model. This study examines whether information from the US carbon futures market is transmitted to the Shanghai carbon market in a stable and linear manner, or whether the transmission pattern changes across different price regimes. My presentation is organized into 5 parts: research motivation, research questions, data and methodology, empirical findings, and conclusions. Carbon trading systems have become important market-based instruments for climate governance and emission reduction. The Shanghai carbon market and the US carbon futures market differ substantially in market structure. Shanghai carbon prices are strongly influenced by compliance cycles, quota allocation, and domestic policy adjustments. In contrast, the US carbon futures market is more derivative-oriented and may contain forward-looking price information. These institutional differences suggest that the relationship between the two markets may not remain constant over time. External information may be transmitted differently when the US futures price is in a lower threshold regime than when it is in an upper threshold regime. A conventional linear model estimates only one average relationship for the whole sample. It may therefore overlook regime-dependent and asymmetric risk. For this reason, this study applies a threshold vector autoregressive model. This study addresses 3 research questions. First, is there a dynamic relationship between US carbon futures and Shanghai carbon allowance prices? Second, does this relationship change across lower threshold and upper threshold price regimes? Third, how do external shocks affect Shanghai carbon prices over time? And how much of Shanghai price variation can be explained by US futures market shocks? The study makes 3 contributions. First, it provides evidence on China-US carbon market interaction, complementing previous studies that mainly focus on EU-China linkage. Second, it uses a threshold VAR framework to capture possible nonlinear and asymmetric transmission. Third, it compares impulse response paths and variance decomposition results across 2 threshold regimes. The main focus is therefore regime-dependent information transmission rather than a single average effect. The empirical analysis uses daily observations from December 2013 to April 2026. The data are obtained from the Shanghai Environment and Energy Exchange and the Intercontinental Exchange. After cleaning and interpolation, the raw dataset contains 3288 observations. The Chinese market variable is the Shanghai carbon allowance closing price. The US market variables include the closing, opening, high, and low prices of ICE listed as carbon futures. Trading volume represents market activity, while the price change rate captures short-term price movement. Before estimation, natural logarithms are applied to the price series. First-order differences are then used to obtain stationary price changes. The observations are sorted chronologically before lagged variables are constructed. The reported results are interpreted together with stationarity tests, lag selection criteria, stability diagnostics, and regime construction. The preliminary time series evidence suggests that the two markets do not follow a stable one-to-one relationship. as carbon futures prices show relatively large movements during several periods. Shanghai carbon prices display plateau-like segments and occasional sharp adjustments. The sample can be divided broadly into 3 stages. From 2013 to 2016, the Shanghai market was still in a pilot stage, and cross-market linkage appeared relatively weak. From 2017 to 2020, market standardization improved, and some same-direction movements began to emerge. From 2021 onward, the relationship appears more regime-dependent as China's national carbon market developed and international market shocks became more important. These stage-specific patterns motivate the use of a nonlinear specification. However, visual evidence alone cannot prove the existence of a threshold effect, so formal econometric testing remains necessary. The main econometric method is the threshold vector autoregressive model, or VAR. A standard VAR model assumes that the same coefficient structure applies to all observations. In contrast, a VAR model allows the dynamic system to switch between regimes according to a threshold variable. In this study, the S-carbon futures closing price is used as the threshold variable. The sample is divided into a lower threshold regime and an upper threshold regime. Each regime has its own coefficient matrix under a common lag structure. This allows the direction, magnitude, and timing of transmission to differ across regimes. The empirical procedure includes data cleaning, unit root testing, lag order selection, threshold splitting, VAR estimation, impulse response analysis, and forecast error variance decomposition. Impulse responses describe the dynamic reaction to shocks, while variance decomposition measures the relative contribution of different shocks. Several diagnostic procedures are conducted before interpreting the VAR results. First, the unit root tests indicate that the original price level series are non-stationary, while their first-order differences are stationary. Second, the archaic information criterion and final prediction error criterion select a lag order of 10 as the reported benchmark. However, a long lag structure increases model complexity. Therefore, shorter lag orders should be examined in future robustness tests. Third, after data transformation and lag construction, the effective estimation sample contains 3267 observations, compared with 3288 observations in the raw dataset. Fourth, both regime-specific systems are reported to satisfy the stability condition. These diagnostics support a preliminary regime-specific analysis. Nevertheless, formal bootstrap threshold tests, alternative threshold variables, and alternative lag structures should be added in the full paper. The main estimation results focus on the Shanghai carbon price equation. In the lower threshold regime, the fifth leg of the S futures closing price is positive and statistically significant. This suggests that external price information may be transmitted to the Shanghai market with a delay. In the upper threshold regime, the fourth leg of the futures price change rate is negative, while the eighth leg of trading volume is positive. This indicates a more complex and channel-dependent adjustment process. Short-term price changes and trading activity may influence Shanghai prices through different time horizons. In both regimes, the lagged Shanghai carbon price remains statistically important. Therefore, the findings do not imply that the Shanghai market is mainly driven by the US market. Instead, they suggest that external information may be transmitted differently across regimes, while domestic price inertia remains a major factor. The impulse response results show different dynamic patterns across the two regimes. In the lower threshold regime, the Shanghai carbon price initially shows a mild negative response to a positive US futures price shock. The response then becomes positive and gradually converges toward zero. In the upper threshold regime, the response is more oscillatory, and the negative component lasts longer. However, the variance decomposition results provide an important qualification. In the lower threshold regime, approximately 99.75% of Shanghai carbon price variation is explained by its own shocks. The contribution of the US futures price shock is approximately 0.03%. In the upper threshold regime, the on-market contribution is approximately 99.90%, while the US futures price contribution is below 0.02%. Therefore, regime differences mainly appear in the timing and shape of the responses. The direct variance contribution of US futures price shocks remains very limited. To conclude, the reported estimates provide preliminary evidence of regime-dependent dynamics between the selected Chinese and US carbon price series. The response paths differ between the lower threshold and upper threshold subsamples. In the lower threshold regime, transmission appears more delayed and moderate. In the upper threshold regime, the response is more oscillatory and channel-dependent. At the same time, Shanghai carbon price fluctuations remain predominantly explained by domestic market dynamics and their own shocks. The results suggest three potential policy implications. First, regulators may develop regime-based monitoring and early warning systems. Second, domestic price stabilization and risk management tools should be strengthened. Third, the development of carbon derivatives may improve price discovery and market resilience. Future research should test alternative lag structures, alternative threshold variables, formal bootstrap threshold tests, and confidence intervals for impulse responses. Thank you very much for your attention. I welcome your questions and comments.